On a cold day in Manhattan, the street can appear to breathe. White vapor rises between taxis. It pours from striped stacks and drifts past buildings worth hundreds of millions of dollars. It looks like steam escaping from the sewer. But beneath the asphalt is something more deliberate, a high-pressure thermal network that has been operating since 1882, and it does far more than heat old radiators. It helps make hot water, control museum humidity, sterilize hospital equipment, and even cool skyscrapers in summer. So why does one of the world's most modern cities still run on steam? The network belongs to Con Edison. According to its 2024 system study, roughly 105 miles of steam mains run beneath Manhattan. They serve about 1,500 customer accounts across a territory stretching from Battery Park to West 96th Street and to East 89th Street on the other side of the island. Those accounts are not 1,500 individual people. Many are enormous buildings, hospitals, hotels, museums, apartment towers, and offices. Con Edison estimates that nearly 3 million people live, work in, or visit the service territory. At winter peak, the system can move millions of pounds of steam every hour. This is not a forgotten Victorian pipe that happens to remain warm. It is active urban infrastructure, operated as a utility and maintained around the clock. The basic idea is older than New York's first skyscrapers. In 1877, an inventor named Birdsill Holly demonstrated a commercially successful district heating system in Lockport, New York. Instead of giving every building its own small boiler, Holly used a central plant. Insulated pipes carried steam to a group of customers, and the amount used could be measured and sold. The proposition was simple: make heat at scale, then move it through the street like water or gas. Investors brought the concept to a much denser market. On March 3, 1882, the New York Steam Company began selling steam in Lower Manhattan. At the time, centralized steam offered several attractions. A customer could avoid storing and handling fuel on site. Buildings could reduce their dependence on individual boiler plants and chimneys. And as Manhattan grew upward, every square foot occupied by machinery became a square foot that could not be rented or used. But the system operating today is not simply the machinery installed in 1882. Its plants, fuels, routes, controls, and customers have changed repeatedly. The network survived by being modified. In the late 1960s and early 1970s, its generating stations moved from coal toward lower sulfur oil. From the 1980s onward, the system added natural gas capability. 2 major stations became fully gas-capable in 2013. The pipes created continuity. Almost everything around them evolved. At its simplest, the system begins with water and heat. New York City water is softened and treated before entering large boilers. Heat changes that water into steam. Most of the fuel used for steam generation is currently natural gas, although some stations can use low-sulfur oil, and the system also receives steam under contract from the Brooklyn Navy Yard. The network is supplied from multiple generating locations rather than one irreplaceable boiler room. Steam enters the distribution mains at high pressure. Con Edison's customer guidance describes saturated steam arriving at approximately 165 pounds per square inch gauge at about 358 degrees Fahrenheit, or 181 degrees Celsius. The important word is not just hot, it is phase. Steam contains energy used to turn liquid water into vapor. When that vapor reaches a building and condenses back into liquid, it releases that latent heat. This allows a comparatively small mass of steam to carry a large amount of thermal energy. Inside a customer building, pressure is reduced and equipment transfers the heat to whatever the building needs. A heat exchanger may warm a closed hot water loop. Coils can heat ventilation air. Other equipment can make domestic hot water or use steam directly for a process. A technical study at the Woolworth building described district steam arriving between roughly 150 and 180 pounds per square inch gauge, then being reduced to much lower pressures for the building's heating and hot water systems. The exact arrangement differs from building to building, but the transaction is the same. Con Edison sells thermal energy at the building boundary. The building decides how to use it. Heating a building with steam is intuitive. Cooling one sounds impossible, but steam can support air conditioning in two main ways. In one design, steam drives a turbine connected to a conventional chiller. The refrigeration process still moves heat out of the building, but the compressor is driven by a steam turbine instead of a large electric motor. In another design, an absorption chiller replaces the mechanical compressor with a heat-driven chemical cycle. A refrigerant evaporates at low pressure and absorbs heat. A salt solution captures that vapor. Steam then supplies the heat needed to separate the refrigerant and restart the cycle. The machinery is more complicated than a window air conditioner, but the strategic benefit is easy to understand. On a hot afternoon, when millions of conventional air conditioners are placing stress on the electrical grid, a large building can use delivered steam for some of its cooling load. Not every connected building does this, but it explains why demand for Manhattan steam does not disappear when winter ends. The same network can provide heat in January and help remove heat in July. Then there are the striped stacks. They are part of steam operations, but they do not always indicate a ruptured steam main. The space beneath a Manhattan street is crowded. Steam pipes share that environment with water, sewer, electrical, and communications infrastructure. When rainwater, a water main leak, or another source of external water reaches a hot steam pipe or manhole structure, it can boil and create visible vapor. A steam leak can also create vapor and must be investigated. The temporary stacks carry that hot vapor above pedestrians, vehicles, and street-level sightlines. That is why the controlled plume can look dramatic while the intervention is routine. But steam is not harmless, simply because the water is clean. At system temperature, it can cause severe burns, and water entering the wrong part of a steam system can produce a far more dangerous effect. On July 18, 2007, a steam main ruptured near East 41st Street and Lexington Avenue, close to Grand Central Terminal. The event opened the street and sent a violent column of steam, mud, and debris into Midtown. The investigation is often reduced to a simple story about an old pipe. The actual mechanism was more revealing. Heavy rain had allowed external water to collect around a deeply buried steam main. That water cooled the pipe, causing an unusually large amount of steam inside it to condense into liquid. A steam trap is supposed to remove condensate without allowing valuable steam to escape, but the drainage capacity of two traps at this location had been impaired. Liquid accumulated inside a pipe carrying fast-moving steam. This created the conditions for a condensation-induced water hammer. Imagine pockets of steam trapped between moving slugs of water. When a steam pocket suddenly condenses, its volume collapses. Water rushes into the space from both directions. The collision produces a short, extreme pressure pulse. Reports commissioned after the incident estimated that pulse at more than 1,200 pounds per square inch, over 7 times the normal operating pressure. The pipe had been installed in 1924, but testing did not support the simple conclusion that it failed because it was old. The immediate problem was abnormal pressure created by water heat transfer, and inadequate condensate removal. That distinction matters. Replacing every old pipe would not remove the physics. A safe steam network must control water, maintain traps, watch conditions, and respond quickly when the underground environment changes. After the incident, Con Edison reported replacing all 1,654 traps then on the system, revising heavy rain procedures, strengthening repair oversight, and expanding remote monitoring. Today, the company says it uses risk models that consider corrosion, flooding, equipment failure, and overpressure. Crews conduct weekly visual surveys, while remote instruments report conditions from parts of the network. The system survives because it is watched, not because old infrastructure can be trusted indefinitely. If the network is old, pressurized, and still burns fossil fuel, why not abandon it and electrify every building? For some buildings, electrification will be the right answer. But Manhattan is not a blank construction site. Large existing buildings can require new electrical service, heat pumps, hot water distribution, backup systems, and major interior work. Mechanical equipment needs physical space. Hospitals and laboratories may need high-temperature process steam that ordinary space heating heat pumps do not provide. The district network moves that complexity away from 1,500 separate customer sites and concentrates part of it at a handful of production locations. It also combines loads that do not all peak in exactly the same way. Con Edison's 2024 study listed about 10.8 million pounds per hour of gross production capacity, compared with a forecast winter peak of roughly 7.6 million. The system is designed around an N-1 principle. Operators maintain enough quick response reserve to cover the loss of the largest steam unit operating at that time, as well as maintenance and unexpected demand. And more than 60% of annual steam production in 2024 was co-generated, made in facilities producing useful steam and electricity from the same fuel input. These are real engineering advantages. They are not an environmental exemption. Con Edison also reported that 98% of the fuel used to generate steam in 2024 was natural gas. The network may use fuel efficiently in certain configurations, but it still carries a substantial carbon problem into the future. This is where the age of the network may become an advantage. The pipes do not care whether their steam was made by coal, oil, natural gas, or electricity. They carry heat. That means the energy source can change at a few central locations while connected buildings continue receiving the same basic product. Con Edison's decarbonization study evaluated 24 technologies. Its near-term concepts included a large electric boiler, an industrial heat pump drawing thermal energy from the East River, thermal energy storage, and improved digital control. An electric boiler would use grid electricity to make steam directly. The proposed industrial heat pump would work differently. Rather than creating all its heat through electrical resistance, it would use electricity to move low-temperature heat from the river to a useful temperature for the steam system. Thermal storage could make heat when electricity is less constrained, then release it when steam demand rises. But a roadmap is not a finished plant. Regulatory filings made in 2025 and 2026 show that these projects are still being separated, costed, and reviewed. One filing reflects a proposed June 2028 in-service date for the electric boiler. Another makes clear that funding for the associated thermal storage concept was not requested in the current steam rate case. And electrifying steam production only cuts emissions as far as the electricity supply, equipment performance, and operating schedule allow. The opportunity is nevertheless significant. Upgrade one central source. and the benefit can flow through existing mains to many difficult buildings. The city does not have to rebuild every customer plant on the same day. That is the enduring logic of district energy. A network can outlive the technology that first fed it. Manhattan's steam system is often described as a relic, but that description misses what makes it interesting. A relic is preserved by resisting change. This network survived by changing its plants, fuels, controls, and safety practices while keeping one useful idea: make thermal energy centrally, then deliver it beneath the street. Its next transformation will be harder. The system must remain reliable while reducing its dependence on fossil fuel. Proposed machinery must survive regulation, construction, economics, and the physical constraints of Manhattan. And every claim of cleaner steam will have to be measured against the real energy used to produce it. But if that transition succeeds, a network born in the age of coal may become a way to move low-carbon heat through a 21st century city. If you want more films about the engineering hidden inside everyday life, subscribe to Built Unseen. The steam rising above the street is not simply New York's past escaping from underground. It is a glimpse of an infrastructure decision the city is still living with and still rewriting.